All right, so for this video, we're going to be talking about some nuances in chemical bonding. And so really central to chemical bonding is this concept of electronegativity that Linus Pauling came up with, right? And so uh, remember from our previous slides that electronegativity is basically the ability of electrons to attract to themselves in a compound, right? And so fluorine is the most electronegative element. It really wants electrons. It's going to win any tug of war versus any other element except itself. Okay, it's a little tie versus fluorine. And so these were the values, right, ranging from the bottom left, rubidium, cesium isn't shown here at 0.7 on francium, and fluorine was the highest at 4.0. Usually the noble gases don't have electronegativity values reported because there aren't many compounds that have these that have noble gases in them. They would have to violate the octet rule, right? They already have uh, 8 valence electrons for the case of neon, argon, krypton, xenon, radon. Helium has 2 because it only has an s orbital, no p orbital. And so for bond polarity, again, you can look at this video online, YouTube video bonding with dogs. It's just kind of cute. Okay. Um, bond polarity is basically a measure of how unequally electrons are shared in a bond. So it's a measure of who's winning the tug of war. Okay. And it's very easy to calculate. All you do is you calculate the difference in electronegativity. So the delta electronegativity is shown here. Okay. And so you can have polar bonds, covalent bonds, and non-polar covalent bonds. And what's the difference? Well, a non-polar covalent bond, you have symmetric distribution of electrons. Basically, the tug of war amongst the electrons in their orbitals is equal. So hydrogen versus hydrogen, they cancel each other out. They're pulling equally strong. They're sharing those 2 electrons in that bond equally. You could draw it like this. A polar covalent bond, one of the elements is going to be more electronegative. In this case, chlorine is more electronegative than hydrogen. So more of the electron density, so I have a bigger kind of blob on the chlorine, representing that more electron density is there and less electron density is on the hydrogen. You can also show these electron density maps. Your books have some of these. Red means like more electrons. They choose some color, okay? It can vary. And blue might mean the hydrogen where there's less electron. But basically, I have an asymmetric tug of war, an asymmetric distribution of electrons in a non-polar covalent compound. It's still sharing, but it's sharing unequally, okay? So if you think about HF, right? If we drew the Lewis structure of that, that's going to be this. We did that as a practice. And look, fluorine is way more electronegative. It's the most electronegative element compared to hydrogen. So you can then calculate the change in electronegativity, or not the change, the difference in electronegativity between the two, 4.0 minus 2.1. I'll always give you these values on the test. Okay, you'll be given a chart if you need it. So the difference, the change in electronegativity, or the difference in electronegativity between the 2 elements there, between hydrogen and fluorine, is 1.9. And so there's going to be much more electron density on the fluorine. We can write that as this lowercase delta. That's a Greek symbol for a lowercase delta, basically, in Greek, with a minus. That stands for a partial charge, the lowercase delta. So we can write a partial minus charge on the fluorine and a partial positive charge, therefore, on the hydrogen. And we draw this arrow. This is called a dipole moment. And it's showing where the negative charge, the electron density, is pointing towards. In this case, it's pointing towards the fluorine. So it's this arrow with this little cross. That is called a dipole moment, okay? And so this has a molecular dipole with a partial negative charge on the fluorine, a partial positive charge on the hydrogen. So a dipole moment is uneven electron sharing in a bond. Change in electronegativity is delta En. And you're always going to do, it's always going to be a positive number here. So it's going to be the larger electronegativity value minus the smaller electronegativity value. Why is it called dipole? It's like the Earth, okay? You know, dipole, like a magnet, okay? That's why it's called that. All right, so we can stop that here, and then next video we'll go into more detail on the different types of bonds.